Imagine walking into a massive library, pulling 3 books off a single shelf, and concluding you understand the entire building's collection. In machine learning, a similar assumption happens every day. Developers typically divide a new dataset into 2 pieces, using 80% of the data to train the model and setting aside the remaining 20% to test it. When the model runs through that isolated 20% and spits out a 96% accuracy score, the initial reaction is usually to celebrate and deploy it. But that single test score hides a major vulnerability known as sampling bias. Data collected from the real world is almost never a perfectly uniform mix. This dataset looks like a single mass, but actually contains hidden subgroups. If a 20% random cut slices right through the most uniform part, the test is rigged. The model looks brilliant, but has only been tested on the easiest examples. Relying on one isolated data split leaves you entirely blind to statistical variance. You aren't measuring the model's true capability, you're just measuring good luck. To strip away that reliance on chance, statisticians use a procedure known as k-fold cross-validation. Here is a graphic showing how it works. Instead of a single cut, the algorithm takes the entire dataset and divides it into a specific number of non-overlapping blocks, often 5 equal pieces. In the first round, the model trains on blocks 1 through 4. Block 5 is held entirely in reserve, acting as the untouched test set. The model evaluates block 5 and returns that highly promising score of 96%. Then the algorithm resets. The isolation zone shifts to block 4, and block 5 gets folded back into the training data. We train a brand new model from scratch and test it on block 4. This time, the accuracy suddenly drops to 82%. The system repeats this cycle until every single block has served exactly once as the test set. We end up with a slate of distinct scores, 88%, 91%, and a low of 79%. That 17-point swing between the best and worst rounds exposes the volatility of the dataset. It proves mathematically that the initial 96% was an illusion created by a lucky split. There is a specific mistake that frequently ruins this process, a flaw statisticians call data leakage. It happens when developers look for the best variables, or perform feature selection, across all of the data before they carve out the k-fold blocks. When you screen variables against the entire dataset first, the test blocks are no longer truly hidden. The predictors have already seen the test samples, giving the algorithm a mathematically unfair advantage. The model will post massive cross-validation scores in the laboratory, but because it actually memorized the noise instead of learning generalizable trends, it collapses instantly when exposed to brand new data in production. For cross-validation to provide an honest assessment, you must lock the test data away in absolute isolation before running any variable selection. We can now return to this graphic showing those 5 wildly fluctuating test scores we generated during the k-fold loop. The final step of the algorithm is to average them all together. This single, stable number is the model's true generalization error. It represents an honest measurement of how the algorithm will actually perform on unseen data. There is a strict computational price for this clarity. Running a 5-fold validation means you have to spend 5 times the computing power to train the model from scratch 5 separate times. But in exchange for that processing time, this method allows researchers to utilize 100% of a scarce dataset for both training and testing without ever letting the model cheat on the exam. Pulling 3 books off one shelf gives you an answer, but it doesn't mean you know the layout of the entire room. The data has been strictly mapped and honestly tested, but sometimes a piece of information refuses to stay where it was placed.